proof writing in algebra. Algebra 1, there's algebraic proofs, and we'll revisit those a little bit. But logic, trying to develop a way to back up your statements, right? Be able to argue more effectively, that kind of thing. Okay? Logic has a very specific form, and we're going to talk about all those forms in the coming days. Okay? So we're going to talk about inductive, and actually we're going to talk about deductive reasoning today as well. And then we'll talk about conditional statements, if-then statements. Okay? And so, inductive reasoning. Inductive reasoning is the process of observing data, recognizing patterns, and making generalizations about those patterns, right? So we're going to use data or patterns to basically make an educated guess about what's going on, right? Different than deductive reasoning, which we're going to talk about in a little bit, which is using facts and recognized assumptions and things like that. Okay, a conjecture is just that generalization. When we make that guess, then that'll be our conjecture. Okay, I keep saying guess. Don't like that word, but it's basically what it is, right? A counterexample. So how are we going to know if our conjectures are true or not? And one way to do that is to do what you do when you argue all the time, is try to poke holes in it, right? Try to find a specific case for which the conjecture is false. And that's going to be your counterexample. So try to find a counterexample, right? So for example, I walk through an apple orchard and all I see are red apples. So the conjecture I make is that all apples are red, right? As far as I know, that's true. So I walk in here and say, hey guys, do you know all apples are red? And you would say, no, why not? I need a counterexample.
Because there's also green and yellow.
Sure, right? So that would be your counterexample for all apples being red. Okay? And easy enough to poke holes in that statement. Okay? Take a look at this. So, if you were a scientist, maybe you're a budding scientist, and you dip a platinum wire into a solution containing salt, or sodium chloride, you pass the wire over a flame and observe that it produces an orange-yellow flame. Then you go back and say, well, that's interesting. And so you start doing this with a lot of other solutions that also have salt in it, and find that the flame is orange-yellow. What conjecture would this little experiment have you making? Right? So, Rain, what would you think?
Salt makes fireball.
Okay, so that would be your conjecture, right? If you burn salt, or if you burn sodium chloride, then you'll get an orange-yellow flame. Okay, good. As far as we know, that's true until it's not, right? Until we find a counterexample. All right? So that's kind of the idea that we get when we're trying to make a conjecture. Okay? And so that was using some data, right? So in recognizing a pattern, nothing we can do, nothing we will do is try to recognize patterns in numbers. So with these two examples, were you guys able to find the pattern? Mandy, what'd you come up with?
I can only figure out A, but
Okay.
it's 2 plus 3 plus 4 plus 5.
And then, so what are the next two numbers?
16 and 22.
16 and 22. Because, like you said, right, we're adding one more every time, right? So we're going plus 2, plus 3, plus 4, plus 5, plus 6. Okay? How about the pattern for B? Rain thinks she's got it. 1/6. How did you discover it's going up 1/6 every time? Because it looks like 1/6, 1/3, 1/2. It's not even keeping the same denominator, right?
Yeah, but it's being simplified.
Ah,
Every time.
okay. So then one thing we might need to do is, in a situation like this, is keep finding common denominators, right? Because like you said, it was simplified. Good. And so the next two numbers would be?
5, 6, and 1.
Good. That's just because we're adding a 6th every time. Okay, good. Good. All right. Yeah, this is going to show the same thing. Okay. We collect data. Okay. We collect data. Here's a graph showing girls' soccer participation. Which conjecture could a high school athletic director make based on the graph at the right? Based on that graph, which of these four would be a good conjecture to make? Shelby, what do you think? B? Is that what you said? B as in boy? Okay, what's wrong with A? And this talks about, right? Okay, good. What's wrong with C?
It doesn't give us information about the World Cup.
Okay, so A and C we can eliminate just because the graph doesn't give us that information, right? What's wrong with D?
False.
It's just false, right? There's more in 95 than there were in 2001? Yeah, no way. So yeah, it's going to be B. Okay. Good. That's kind of what we do with inductive reasoning. Okay. A lot of our conjectures can be written in what's called a conditional statement. Okay? A conditional statement is a logical statement that has two parts. It will have a hypothesis and then a conclusion. Okay? Conditional statements can be written in really any form, right? I mean, a sentence structure, or in this thing called an if-then form. Just about any sentence can be a conjecture. Just about any sentence can be written in if-then form. Okay? If we take our conditional statement and want to try to put it in if-then form, then our two parts, hypothesis and the conclusion. The hypothesis will be the if part, right? And then the hypothesis will be your condition, right? This has to happen in order for this to happen, right? If I have an apple, okay, that's your condition. Your conclusion will be what follows the then. Okay? If I have an apple, or if this fruit is an apple, then it is red. Okay? Now, they don't have to be true. They'll be true or false. Sometimes it's very concrete, whether they're true or false. Sometimes not so much. Okay? But that's what we're talking about. Trying to write things in if-then statement, an if-then form. And if we take a statement and want to try to write it in if-then form, you want to be careful not to change the statement, right? It's got to say the same thing, just got to be in a different form. And you don't want to add anything, you don't want to add too much to that statement. And we'll see that it's not always as easy as it seems. Okay? So, try to rewrite this conditional statement in if-then form. The car runs when there is gas in the tank. If you want to write that in if-then form, what do you think that might sound like? Okay? Kaylin, what do you think it's going to sound like?
If there is gas in the tank, the car will run.
Good. If there is gas in the tank, then the car will run. Okay? Having gas in the tank is going to be your condition, and then your conclusion will be the car will run. Okay? Is that true or false?
Depends on what's under the hood, because, there could be a belt loose or something.
So then that would be your counterexample, right? Right? So if there is gas in the tank, then the car will run. Is that necessarily true? No. Okay? That's all right. We'll worry about true, false stuff later. Okay? Second one, there are 12 eggs if the carton is full. Be careful. If there are 12 eggs, if the carton is full. Daniel Hood, what do you think? Well, I need an if-then statement.
If there are 12 eggs, then the carton is full.
Okay, if there are 12 eggs, then the carton is full. Not exactly the same thing that that sentence is saying, right, Aaron? What is it saying?
The carton is full and there are 12 eggs.
That's it. That's it. If the carton is full, then there are 12 eggs. Okay? And in the original statement, there are 12 eggs if the carton is full. The carton being full was your condition. Okay? So be careful there. If the carton is full, then there are 12 eggs. Is that true or false? False?
They can go up to 32 eggs.
It didn't specify what kind of carton, right? Okay. All right. Good. Now, what Daniel did, Shelby and Pete were talking about, those are different types of conditional statements. If-then statements, keep talking about those guys. A negation. What do we mean by negating something? A negation is a statement that is the opposite of the original statement. Okay? If I wanted to negate something, I wanted to make it opposite. All apples are red. To negate that, we simply say all apples are not red. Yeah, that's basically it. Okay? Now, in your if-then statements, once we create a conditional statement, we can create what's called the converse. And all we have to do to make a converse is to flip-flop the hypothesis and the conclusion. Okay? Interchanging the hypothesis and the conclusion, as we've seen, can change a conditional statement from being true to false or from false to true. Might not change it at all. Okay? But to make a converse, we just got to flip-flop, right? To make the inverse. To make the inverse, you want to negate both the original hypothesis and the original conclusion in your original conditional statement. Okay? 9 times out of 10, that's going to simply be inserting the word not into your hypothesis and conclusion, as long as it makes sense grammatically. Okay? And then there's this thing called the contrapositive. The contrapositive is when you write the converse, but then you negate both the hypothesis and the conclusion. Okay? Okay? Got those? Okay. Try to write some of these. Okay, write the if-then form, the converse, the inverse, and the contrapositive of the conditional statement, soccer players are athletes. At least according to what that sentence says. True or false? False?
All right, go ahead.
Okay. And the point here is, and I don't know seriously if you'd want to try to argue that soccer players are not athletes, but if you put race car driver in there, then I would probably argue with you that would be false, right? The point is, some if-then statements may not be so concrete on whether they're true or false, right? Kind of depends on how you look at it. Yep.
Well, you could say that if they're a soccer player, they don't always play the soccer. They just sit on the side or something.
True, but would that stop them from being an athlete?
They aren't athletic.
So that means that the quarterback of our football team, when we're on defense, is no longer an athlete. Is that what you're saying? Okay, hang on a minute. A little less ambiguous, right? What about what do we need then? We need the converse. How about the converse of this statement? Ashley?
You are an athlete if you are a soccer player.
Okay, you are an athlete if you are a soccer player. Did you really change? Did you really flip-flop the hype? Okay. If you are an athlete, then you are a soccer player, or if you are an athlete, then you must play soccer. Okay. I think a little bit more concretely, is that true or false? Because
There's football players, basketball players, baseball players.
right. What's that?
Ultimate frisbee players.
Right.
Just throwing that out there.
Right,
Throwing it at the time.
Yeah, yeah.
Sounds like a hobby. Yeah, it's more of a hobby.
Good. If you're not a soccer player, if you didn't play soccer, then you're not an athlete. Okay, I think both say basically the same thing. Right? If you're not a soccer player, then you're not an athlete. True or false? For the same reason as the converse, right? And then the contrapositive. Riley, the contrapositive would sound like what? You didn't get that one. How do you create the contrapositive, Riley?
You write the converse and then negate both the hypothesis and conclusion.
Right. to look at the converse, how would you negate the hypothesis and the conclusion? What's the opposite of if you are an athlete? Beautiful. What's the opposite of then you are a soccer player? That's it. That's all you got to do. Okay? That's it. If you're not an athlete, then you're not a soccer player. Yes?
You said if you're not an athlete and you don't play soccer.
Same thing, right? I think that's basically the same thing. Yeah. What's that?
I'm not saying it's true because if you don't play, if you're not an athlete, then you don't play sport.
I would say that's probably true. I would say that's probably true. Noah's in a particularly argumentative mood today.
I'm not quite sure what he said.
Exactly. He's just going to argue. All right, good. Moving on. A biconditional statement. A biconditional statement is a statement that contains the phrase if and only if. Okay? If and only if. And you're going to see those biconditional statements fairly often when we start talking about different postulates and theorems in here. Okay? You can use a biconditional statement when both the conditional statement and its converse are true. If your conditional statement's true and then you flip-flop the hypothesis and the conclusion, and it's still true, then we use the phrase if and only if, and we call it a biconditional statement. Okay? So think about and write out the conditional statement and the converse for the definition of perpendicular lines. And there's your biconditional statement. Two lines are perpendicular if and only if they intersect to form right angles, to form a right angle. You didn't do that. What'd you do?
Two lines intersect to form right angles, then the two lines are perpendicular.
Okay, good. If two lines intersect to form a right angle, then they are perpendicular. And that's true, right? The conditional statement is true. Okay, if two lines intersect to form a right angle, then they are perpendicular. That would be your conditional statement. Okay, intersecting to form a right angle is your condition. I hear some of you guys are racing. Okay. That part of the biconditional statement is following the if. That can be your clue to make that your hypothesis in your conditional statement. Okay? And then the converse. We want to make sure that the converse is true. Okay, Megan? And the converse would sound like... Okay, good. If two lines are perpendicular, then they intersect to form a right angle. And that's true as well. Okay, since both of those are true, we create that biconditional statement. All right? Any major issues with that? All right. We'll skip this just for a second. I'm going to carry on to section 2.3. It's not very long. Okay? And try to get us caught up a little bit here. 2.3 is now talking about deductive reasoning. Remember, inductive reasoning is using patterns and data to make some conjectures, right? Very educated guesses. Okay? Deductive reasoning is the process of showing that certain statements follow logically from agreed upon assumptions and proven facts. Okay? Deductive reasoning is a logical, sequential way of going from point A to point B in a thought process, using agreed upon assumptions and proven facts. Okay? In a lot of debates or disagreements, deductive reasoning is the first thing that goes out the window. Right? People tend to want to use inductive reasoning. Patterns. Sometimes data, but not even very often then, right? But deductive reasoning is where you find your strength. Okay? Tell me whether the statement is the result of inductive reasoning or deductive reasoning. Is the statement coming from a recognized pattern, or what we can pull from the data, or is it from proven facts? Okay? Again, not what you have in your notes here. But we have this sea lion, right? Seal. Whatever that thing is. Right, we have a graph here, strokes used to the surface. Okay? So if we made this conjecture, the northern elephant seal requires more strokes to surface the deeper it dives. Would that be an example of inductive or deductive reasoning? Daniel, what do you think? Deductive? Why deductive? We're using proven facts and agreed upon assumptions to make that statement?
Yeah, the lower you go, the more effort you have to use to get back up.
Okay. If it were a proven fact, would you have those dots in the graph scattered so much? Because apparently it looks like for some northern elephant seals, they didn't require as many strokes to be at the same depth, right? Okay, but if it were a proven fact that it's going to take more strokes the deeper they dive, would those dots be scattered so much? Would your data be scattered so much? Okay, so then Mandy?
Wouldn't it be like it's inductive because we were using data?
Right. And that's what I'm getting at, right? We're using the data in a pattern here, recognized pattern, which is what Daniel was talking about, to make that statement. So this guy is going to be, we're using inductive reasoning. Okay, good. Okay, if we were to say the northern elephant seal uses more strokes to surface from 250 meters than from 60 meters, okay, then we would be using your deductive reasoning. Okay, and you can do that just by finding the two data points in your graph, right? At 60 meters is this guy right here, and at 250 is this guy right here. Okay? So there's your deductive reasoning. All right? Some more here. Tell whether the statements are deductive or inductive reasoning. Okay? Take a look at these. If we say Angela knows that Walt is taller than Pete, she also knows that Peter is taller than Natalie. So then Angela reasons that Walt is taller than Natalie. Is that inductive or deductive? Deductive. Right? She knows. She knows. These are proven facts. Okay? So deductive, right? Number 2, Josh knows that brand X computers cost less than brand Y computers. All other brands that Josh knows of cost less than brand X. Josh reasons that brand Y costs more than all other brands. Okay? Because all of the brands that Josh knows of, right? He's using a pattern there. Every other brand that he's looked at, brand X costs more. Okay? Okay, so definitely. And then 3, for the past 3 Wednesdays, the cafeteria has served mac and cheese for lunch. Therefore, Dana concludes the cafeteria will serve mac and cheese for lunch this Wednesday. Right, again, we're using a pattern. Dana's recognized the pattern of Wednesdays being mac and cheese day. Right? So that's going to be your inductive reasoning. The last one, if you live in Nevada and are between the ages of 16 and 18 and you must take driver's education to get your license. Anthony lives in Nevada, is 16 years old, and has a driver's license. Therefore, Anthony took driver's education. And that's going to be, okay, deductive reasoning. Those are all proven facts. Those are all facts that you can prove. Okay? All right? We kind of see the difference there? Okay? All right, there are a couple of laws we're going to talk about, and then we'll be done. All right? A couple of laws of logic that we're going to talk about, and then we'll be done. The first one is what's called the law of detachment. Okay? In the law of detachment, if the hypothesis of a true conditional statement is true, then the conclusion is also true. Okay? Right? And the definition is a little confusing, but if the hypothesis of a true conditional statement is true, then the conclusion is also true. Okay? If a car runs, then there is gas in the tank. Right? That's a true conditional statement. So if you put the key in the ignition and start the car up, so the car runs, which is your hypothesis is now true, the car is running, that means the conclusion has to be true. You don't have to pop open the gas cap and check to make sure there's gas in the car. You know that there's going to be gas in the car. Okay? Right? So, to that point, we can use the law of detachment to make a valid conclusion in a true situation without actually knowing. Right? Like that. We don't necessarily, put a dipstick down in the gas can and make sure there's gas in the tank. We know that there is gas in the tank. So, for this example, Mary goes to the movies every Friday and Saturday night. Today is Friday. You would conclude, yeah, she's going to the movies. Okay? And you would conclude that Mary is going to the movies. Okay? All right? That's the law of detachment. Okay? I don't know what easy way to remember that. The conclusion's been detached. You don't know if the conclusion is true or not. But if the conditional statement is true and the hypothesis happens, then you know the conclusion's going to happen without needing to check on it. Okay? I know there's one way to think about it. Right? Then there's something called the law of syllogism. In the law of syllogism, it becomes really helpful to start using symbols for your statements. Okay? So when you see the law of syllogism and it says P, Q, and R, those are just hypotheses and conclusions. Okay? And it could be anything. Right? Okay, for example, if a fruit is an apple, then it is red, right? Then we would let this part be P and this part be Q. Okay? So P, Q, and R are just different statements that we were using for a hypothesis or a conclusion, right? What the law of syllogism says is if you have two statements, if the hypothesis P, then conclusion R. So if P, then Q, I said R, I meant Q. If P, then Q, and then the next statement, if you use the conclusion from the first one as the hypothesis for the second one to make another conclusion, so if Q, then R, and those two statements are true, then you can jump from P to R, and it's still going to be true. If hypothesis P, then conclusion R. If you take the words out of that, it makes a little bit more sense, I think, and we can just use symbols, right?
Yeah.
We can write it like, if P, then Q, if Q, then R, and these two are true, and we know that these two are true, then the law of syllogism says, well then, without even knowing for sure, we can jump from saying, if P, then R. And we know that that's going to be true. That's what the law of syllogism says. Okay? It's a lot like the algebraic property, A equals B, B equals C, therefore A has to equal C. It's kind of the same thing. Okay? But we have to use the conclusion from the first conditional statement as the hypothesis for the second conditional statement. And then these two, the first two statements, A and B, have to be true. Okay? So, if we were to use the law of syllogism, if possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. Right? If Rick takes chemistry this year, that would be the P. Then Jesse will be Rick's lab partner, which is going to be your Q. If Jesse is Rick's lab partner, that's your Q again, right? Then Rick will get an A in chemistry. There's a new conclusion we can let be R. And we see up there at the top that those two statements are true. Okay? So based on those two statements, conclusion you can make would be what? We're going to use P to help us conclude R. We're going to jump straight from P to R. And therefore, we're going to be able to say, if Rick takes chemistry this year, then Rick will get an A in chemistry. Okay? And we know that's going to be true. Right? But the conclusion of the first statement has to be the hypothesis of the second statement. Okay? Now, if possible, use the law of syllogism. Second example, if a polygon is regular, then all angles in the interior of the polygon are congruent. If a polygon is regular, then all of its sides are congruent. Can we use the law of syllogism here? Okay? If a polygon is regular, that's going to be your P, right? All angles in the interior of the polygon are congruent. That's your Q. Now, in the next statement, your hypothesis should be the conclusion from the first statement. Is it? No. We're using the hypothesis from the first statement again as the hypothesis for the second statement. And this is going to be our R. Okay. So can we use the law of syllogism? No. Right? Neither statement's conclusion is the same as the other statement's hypothesis. So we're not going to be able to use the law of syllogism to write a new conditional statement. Okay? Trying to see how that works?